What if I told you that the simple act of accelerating a single atom to the speed of light could unleash enough energy to obliterate our solar system? Not through some science fiction weapon, not through antimatter explosions, but through the fundamental mathematics of Einstein's relativity. Every single particle physicist knows this terrifying truth, yet we rarely talk about what it actually means. Here's something that will shake everything you think you know about physics. The faster you move, the heavier you become. Not metaphorically, literally, your mass increases. And at the speed of light, your mass becomes infinite. An infinite mass means infinite energy. Infinite energy concentrated in a single point creates what physicists call a catastrophic singularity, a tear in the fabric of spacetime itself. But here's where it gets absolutely insane. We're not just talking about one object. Every photon, every light particle zipping through the universe right now is traveling at light speed. So why hasn't the universe destroyed itself? The answer to that question will completely change how you understand reality, energy, and the very structure of existence. By the end of this video, you'll understand why the speed of light isn't just a speed limit. It's the universe's emergency shutdown mechanism, the one thing preventing reality from collapsing into infinite chaos. Before we dive deep into this rabbit hole, smash that like button if you're ready to have your mind completely rewired. Subscribe and hit the notification bell, because what we're about to explore will fundamentally change how you see the world around you. And I want to know, where are you watching this from? What country? What time is it there? Drop it in the comments, because this is a global conversation about the most fundamental laws that govern all of our existence, no matter where you are. Let's start with something that seems simple, but hides a universe of complexity. Speed. You think you know what speed is, right? Distance divided by time. If you drive 60 miles in 1 hour, you're going 60 miles per hour. Elementary school mathematics. But here's what they don't tell you in school. Speed isn't just about how fast you're moving. It's about how reality itself functions around you. When you move faster, time literally slows down for you. Space literally contracts around you. And your mass, the fundamental property that makes you, literally increases. This isn't philosophy. This isn't metaphor. This is measurable, testable, proven physics. In 1971, physicists Joseph Haffel and Richard Keating took 4 atomic clocks, the most precise timekeeping devices ever created, and flew them around the world on commercial airliners. When they compared these clocks to identical clocks that stayed on the ground, the flying clocks were behind by exactly the amount Einstein's equations predicted. Time had literally moved slower for those clocks because they were moving faster. We're not talking about malfunction. We're talking about atomic clocks accurate to billionths of a second, all showing the exact same discrepancy. Think of it like this. Imagine you're standing still, and the universe is a giant fabric stretched out around you. Now imagine you start running. That fabric doesn't just stay still. It warps. It compresses in front of you and stretches behind you. The faster you run, the more extreme this warping becomes. At everyday speeds, this warping is so tiny we can't detect it. But as you approach the speed of light, which is 186,000 miles per second, this warping becomes so extreme that it fundamentally changes your relationship with reality itself. Albert Einstein figured this out in 1905 when he published his special theory of relativity. He was 26 years old, working as a patent clerk in Switzerland, and he completely revolutionized our understanding of the universe. Einstein asked a simple question. What would happen if I chased a beam of light at the speed of light? Would the light appear to stand still? His answer was shocking. No. Light would still appear to move at exactly the same speed, 186,000 miles per second, no matter how fast you were moving. This seems impossible. If you're running at 10 miles per hour and someone throws a ball at you at 20 miles per hour, you experience the ball coming at you at 30 miles per hour relative to the ground. But light doesn't work that way. Light always moves at exactly the same speed, regardless of how you're moving. This led Einstein to a mind-bending conclusion. If light speed is constant for everyone, then time and space must be flexible. They must warp and change to keep light speed constant. When you move faster, your time slows down and your space contracts in exactly the amounts needed to keep light speed the same for you as it is for someone standing still. This isn't just theory. Every GPS satellite orbiting Earth right now has to account for time dilation, or your navigation would be off by miles within minutes. The satellites are moving fast enough and experiencing different gravity than we are on the surface that their clocks run at different rates. Engineers programmed corrections into the system based on Einstein's equations, and it works perfectly every single day. But here's what will blow your mind. Time dilation and space contraction are just the warm-up. The really terrifying part is what happens to mass. In Einstein's equations, there's a factor called the Lorentz factor. It's written as gamma, and it tells you how much time dilates, space contracts, and mass increases as you speed up. At low speeds, gamma is basically 1. Nothing changes. But as you approach light speed, gamma starts climbing. At 90% of light speed, gamma is about 2.3. Time moves at 43% of normal speed for you. Your mass is 2.3 times heavier. At 99% of light speed, gamma is about 7. At 99.9%, gamma is 22. Now here's where mathematics becomes nightmare fuel. At exactly 100% of light speed, gamma becomes infinite. Not a big number, literally infinite. Division by 0, mathematical impossibility. Your mass would be infinite. The energy required to move you would be infinite. You would contain all the energy in the entire universe, and it still wouldn't be enough. This is why physicists say nothing with mass can reach light speed. It's not a technology problem. It's not that we haven't built powerful enough rockets. It's that the universe's fundamental mathematics says no. This is impossible. This breaks reality. But wait, you're thinking, what about light itself? Photons travel at light speed all the time. They're doing it right now, bouncing off this screen into your eyes. How do they do it? Here's the beautiful, elegant answer that makes everything click into place. Photons have zero rest mass. They have no mass when they're standing still. They can never stand still. They're born moving at light speed, and they die moving at light speed. They experience zero time. From a photon's perspective, it's emitted and absorbed in the same instant, even if it travels across the entire universe. 13 billion years to us is 0 seconds to the photon. This is why matter and light are fundamentally different categories of existence. Matter can never reach light speed. Light can never travel slower than light speed. They're separated by an unbridgeable mathematical infinity. But here's the question that should be burning in your mind right now. What happens if we try anyway? What if we somehow, impossibly, pushed an object with mass to exactly light speed? What would actually happen? The answer is so much worse than you think. And that's where we're going next. Imagine this scenario. Let's say scientists build the most powerful particle accelerator in history. We're talking about a machine that makes the Large Hadron Collider look like a toy. This machine accelerates a single proton, one of the fundamental particles that makes up atoms, closer and closer to light speed. Right now, the LHC can accelerate protons to 99.999991% of light speed. At that velocity, the proton's mass is increased by about 7,000 times. A single proton gains the mass of a grain of sand. When it collides with another proton, the energy release is so intense, it creates showers of exotic particles, and sometimes even generates miniature black holes that evaporate instantly. But let's push further. Let's imagine we could get to 99.999999999% of light speed. At this velocity, the Lorentz factor gamma becomes astronomical. That single proton now has the mass equivalent of a car. Keep pushing. 99.999999999%. The proton now masses as much as a mountain. The energy required to push it even a tiny bit faster now equals the output of our sun for an entire year. Here's what absolutely nobody tells you in school. That energy doesn't come from nowhere. It's converted directly from the work you're putting into accelerating the particle. Einstein's famous equation E equals mc squared works both ways. Energy can become mass, and mass can become energy. As you pump more energy into accelerating this proton, that energy literally transforms into mass. The particle gets heavier, which means it requires even more energy to accelerate further, which makes it even heavier in an endless exponential spiral. Now imagine the impossible. We reach exactly 100%. 100% of light speed for an object with rest mass. The mathematics says the mass becomes infinite. An infinite mass concentrated in a single point. Do you know what infinite mass in a single point is called in physics? A singularity. The same type of singularity that exists at the center of black holes. The same type of singularity that existed at the moment of the Big Bang. You would create a point in space with infinite density, infinite gravity, infinite curvature of spacetime. Everything around it, light, matter, space itself, would be sucked into this singularity. The gravitational pull would be so intense that it would tear apart atoms, rip electrons from nuclei, and compress everything into an infinitely dense point. This isn't speculation. This is what Einstein's field equations tell us would happen. You would literally create a black hole with infinite mass, and that black hole's event horizon, the boundary beyond which nothing can escape, would expand at the speed of light in all directions. But here's where it gets even more terrifying. Remember, we're talking about an object with infinite energy. That energy has to come from somewhere. If you somehow pumped infinite energy into accelerating this particle, you would be drawing on every joule of energy in the entire universe. The entire cosmic energy budget would be concentrated into this one point. Stars would wink out. Galaxies would go dark. All the light, all the heat, all the nuclear reactions powering every sun in every galaxy would drain away, funneling into this single catastrophic acceleration. Stephen Hawking explored scenarios like this in his work on singularities in the 1960s and 70s. He and Roger Penrose proved mathematically that singularities are inevitable when you compress enough mass and energy into a small enough space. Their singularity theorems showed that once you cross certain thresholds, the formation of a singularity is unavoidable. The universe's own laws guarantee it. This work earned Penrose the Nobel Prize in Physics in 2020. Think of it like a drain in space-time. Normally, energy and matter flow around the universe relatively smoothly. But create a singularity, and you've punched a hole in the fabric of reality itself. Everything spirals toward that hole, faster and faster, until space-time itself tears apart. The technical term is geodesic incompleteness. Paths through space-time simply end. They don't go anywhere else. They just terminate at the singularity. Now here's a question that might be forming in your mind. If this is so catastrophic, why does the universe allow light to travel at light speed? Why don't photons create singularities? The answer reveals something profound about the structure of reality. Photons don't have rest mass. They have energy and momentum, yes, but not rest mass. The equations that produce infinite mass at light speed only apply to objects with rest mass. Photons slip through a loophole in the mathematics. They exist in a category of things that must always move at light speed, never faster, never slower. But there's another layer to this. Photons do have relativistic mass, mass from their energy and momentum. And when enough photons are concentrated in a small enough space, they absolutely can create a black hole. This is called a Kugelblitz, a black hole made entirely of light. If you could somehow focus enough laser beams into a small enough point, the combined energy density would warp spacetime so intensely that it would collapse into a black hole. No matter required. Pure light creating a gravitational trap is so powerful that even more light can't escape. Physicist John Wheeler explored this concept in the 1950s and 60s. He showed that energy and mass are equivalent when it comes to gravity. A sufficiently intense electromagnetic field can curve spacetime just as effectively as matter. The universe doesn't care whether you're concentrating matter or energy. If you pack enough of either into a small enough space, you get a black hole. So here's the horrible irony. The speed of light is simultaneously the safest speed in the universe for things meant to travel at that speed, and the most dangerous speed for anything else. It's a boundary written into the fundamental fabric of reality. Cross it with mass, and you trigger existential collapse. Stay on the right side of it, and reality remains stable. But I promised you something even more mind-blowing. What if I told you that this isn't just about protecting the universe from catastrophic singularities? What if the speed of light being an absolute limit is actually the only reason causality, cause and effect, works at all? What if breaking the light speed barrier wouldn't just destroy space, it would destroy time itself? That's where we're going next, and trust me, this is where reality gets truly stranger than fiction. You need to understand something crucial about time. We think of time as flowing from past to future, like a river that only moves in one direction. We remember yesterday, experience today, and anticipate tomorrow. This seems so obvious, so fundamental, that we rarely question it. But here's what will absolutely shatter your comfortable assumptions about reality. The direction of time is directly connected to the speed of light limit. If you could go faster than light, past and future would become meaningless. Cause and effect would break down. You could receive messages before they were sent. You could kill your grandfather before your father was born. The universe would descend into logical paradox and temporal chaos. Let me show you exactly how this works. Imagine two events happening in space. Event A, a star explodes. Event B, 10 light-years away, an astronaut sees the explosion. From our perspective on Earth, these events have a clear order. The star explodes first, and 10 years later, the light reaches the astronaut. Cause precedes effect. But here's what Einstein realized that nobody before him understood. Different observers moving at different speeds see these events in different orders. If you're standing still relative to the star, you see it explode, then see the light reach the astronomer 10 years later. But if you're moving toward the star at a significant fraction of light speed, due to relativity of simultaneity, you might see the astronomer receive the light before the star explodes from your perspective. Now, this seems like just a weird trick of perception. After all, the light still takes time to travel, so causality is preserved, right? Wrong. Here's where it gets insane. As long as both observers are moving slower than light, there's a limit to how much they can disagree about the order of events. Events that are causally connected, where one directly causes the other, always maintain their order for all observers. The explosion must happen before the light arrives. Everyone agrees on this. The mathematics of spacetime has a structure called the light cone. Any event that happens can only directly affect other events within its future light cone, the region of spacetime that light from that event can reach. And it can only be directly affected by events in its past light cone, events that could send light signals to it. But if you could travel faster than light, you could step outside your light cone. You could reach places that light from your starting point hasn't reached yet. And here's the killer. Once you can move faster than light, you can create closed time-like curves, loops in time. You could literally travel back to your own past. Here's how it works, and this is real physics, not science fiction. Let's say you have a ship that can travel at twice the speed of light. You leave Earth heading toward a star 10 light years away. From Earth's perspective, you arrive in 5 years. Now, here's the crucial part. Due to relativity of simultaneity, different reference frames disagree about when things happen. From your ship's perspective at twice light speed, assuming the impossible, the mathematics shows that you could turn around and return to Earth, arriving before you left. Physicist Herbert Dingle, and later Paul Davies, worked through these scenarios mathematically in the mid-20th century. They showed that faster-than-light travel necessarily creates situations where effect precedes cause. You could shoot yourself before you pulled the trigger. You could prevent your own departure while you're already en route. The universe would be filled with paradoxes, logical contradictions that can't be resolved. Think of it like this. Causality, the principle that causes precede effects, is like a web connecting all events in the universe. When you're limited to light speed or slower, this web has a coherent structure. Event A connects to event B, connects to event C in clear chains. But faster-than-light travel lets you reach back and cut threads, reconnect them in different orders, create loops and tangles. The web collapses into chaos. The universe can't maintain a consistent history. Some physicists argue that the universe would prevent paradoxes through some unknown mechanism. Maybe timelines branch, creating parallel universes. Maybe something called chronology protection prevents closed time-like curves from forming. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time machines from being built. But here's the thing. We don't know. We have no experimental evidence. We only know that in our universe, nothing with mass can reach light speed, so we never have to deal with these paradoxes. But the implications go deeper. If faster-than-light travel were possible, information could travel backward in time. And information traveling backward in time means entropy, disorder, could decrease locally. The second law of thermodynamics says entropy always increases. Hot things cool down. Ordered things become disordered. The universe marches toward heat death. But if information can loop back, you could create perpetual motion machines, violate energy conservation, and generally break every fundamental law of physics we've discovered. The physicist Richard Feynman once described antimatter as matter moving backward in time. When an electron and positron annihilate, Feynman said you could view it as a single electron bouncing backward in time, being its own antiparticle. This was brilliant mathematical insight, but it only works because these particles are still moving within the light cone. They're not truly violating causality. But faster-than-light particles, hypothetical tachyons, would genuinely move backward through time in a way that creates real paradoxes. Here's a thought experiment that demonstrates the horror of this. Imagine you have a faster-than-light communicator. You send a message to your friend on Mars, traveling at twice light speed. Your friend, also moving in her own reference frame, sends a reply at twice light speed. Depending on the relative motions involved, her reply could reach you before you sent your original message. You receive her answer before you ask your question. Now, what if her answer is, "Don't send that message"? Do you send it or not? If you don't send it, she never replies, so you never receive the instruction not to send it. So you do send it, so she does reply. Infinite loop. Reality crashes. This is called the tachyonic antitelephone paradox, worked out by physicist Gregory Benford and others in the 1970s. It proves mathematically that faster-than-light communication necessarily creates temporal paradoxes if special relativity is correct. And special relativity has been confirmed by literally thousands of experiments over more than a century. It's one of the most tested, most verified theories in all of science. So the speed of light isn't just protecting us from infinite energy singularities, it's protecting causality itself. It's the firewall between a universe where effects follow causes and a universe of paradox and chaos. Breaking that barrier wouldn't just destroy space, it would destroy time. Past, present, and future would blur into a nonsensical mess where nothing can be said to happen before or after anything else. Now, I know what you're thinking. This is terrifying, but it's all theoretical, right? We can't actually accelerate anything to light speed, so we're safe. The universe's mathematics protects us. But here's what will keep you up tonight. There are scenarios, rare but possible, where the universe itself creates these conditions, where nature might actually test the limits of these laws. And in those scenarios, we've seen hints, just hints, that reality might be more fragile than we ever imagined. Stay with me, because what I'm about to show you suggests that the universe has come terrifyingly close to destroying itself, and might do so again. Let's talk about cosmic rays. Right now, as you watch this video, particles from space are raining down on Earth at velocities so close to light speed that they make our best particle accelerators look pathetic. In 1991, scientists detected a single cosmic ray particle with energy of 320 quintillion electron volts. To put that in perspective, this single subatomic particle had the kinetic energy of a baseball thrown at 60 miles per hour. One particle, with as much energy as a macroscopic object. This particle, dubbed the "Oh my God" particle by the astronomers who detected it, was traveling at 99.999999999999998% of the speed of light. At this velocity, the Lorentz factor gamma is about 320 million. Time dilation is so extreme that from the particle's reference frame, it crosses the entire Milky Way galaxy in less than 1 second. From our reference frame, that journey takes 100,000 years. But to the particle, the entire galaxy is compressed to a pancake about 30 feet thick due to length contraction. Now, here's the terrifying question. Where did this particle come from, and what accelerated it to this absurd velocity? We don't know. The most powerful cosmic accelerators we know of are supermassive black holes at the centers of galaxies, spinning at relativistic speeds and flinging matter outward in jets. But even those shouldn't be able to reach these energies, according to our standard models. There's something out there in the universe capable of pushing particles to energies that approach the theoretical limits of what spacetime can handle. And here's what makes physicists nervous. There's a theoretical maximum energy for particles called the Planck energy. At this scale, about 10 to the 19 billion electron volts, the wavelength of a particle becomes so small and its energy so concentrated that quantum effects of gravity become important. At this energy, we expect spacetime itself to fluctuate and foam at quantum scales. The smooth fabric of reality breaks down into something more like quantum foam, with microscopic black holes spontaneously forming and evaporating. The "Oh my God" particle had energy about 1/trillionth of Planck energy. That sounds safe, but remember, this is a single particle. Now imagine if we could accelerate not just one particle, but a beam of billions of particles to these energies. Or imagine if nature, somewhere in the universe, has found a way to concentrate even more energy into a single particle. We're approaching the edges of where our physics breaks down, where the equations start producing infinities and nonsense. Here's something even more unsettling. The "Oh my God" particle shouldn't exist according to something called the GZK cutoff. Physicists Kenneth Greisen, Vadim Kuzmin, and Georgy Zatsman predicted in the 1960s that ultra-high energy cosmic rays should interact with the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. These interactions should slow the particles down and create a maximum energy for cosmic rays reaching Earth. The "Oh my God" particle exceeded this limit. It shouldn't have been able to reach us. Either it was created much closer than we think, within our own galaxy, which means there's an unknown ultra-powerful accelerator nearby, or something about our understanding of particle physics at these extreme energies is wrong. Other ultra-high energy cosmic rays have been detected since, dozens of them, all violating the GZK cutoff. Scientists call these particles trans-GZK cosmic rays. The Pure Auger Observatory in Argentina detects about one such particle per year. Each one is a mystery. Each one represents energies that challenge our understanding of what's possible in this universe. But cosmic rays are just the beginning. Let's talk about something even more extreme: particle collisions inside neutron stars. A neutron star is what's left when a massive star explodes in a supernova, but isn't quite heavy enough to become a black hole. The core collapses until neutrons, normally found inside atomic nuclei, are crushed together so tightly that they touch. The entire mass of a star, bigger than our sun, is compressed into a sphere about 12 miles across. A teaspoon of neutron star matter weighs about 1 billion tons. Inside a neutron star, matter exists in states we can barely comprehend. The pressure is so intense that atomic nuclei are shattered. Electrons are forced to merge with protons, creating more neutrons. In the very core, some physicists believe matter might break down even further into a sea of free quarks, the fundamental particles that make up protons and neutrons. This hypothetical state is called quark matter or strange matter. Here's where it gets apocalyptic. When neutron stars collide, and we've observed this happening with gravitational wave detectors, the energies involved are absolutely staggering. Particles collide at velocities that make our particle accelerators look like slow motion. The matter is compressed to densities that might actually reach quantum limits. And in those collisions, we might be creating conditions where particles approach light speed with enormous mass. In August 2017, gravitational wave detectors LIGO and Virgo detected the merger of two neutron stars. This event, designated GW170817, released more energy in the form of gravitational waves alone than the Sun will produce in its entire 10 billion year lifetime. And that's just the gravitational waves. The actual explosion released a gamma-ray burst, a beam of electromagnetic radiation so intense that if it were pointed directly at Earth from anywhere in our galaxy, it could strip away our ozone layer and cause mass extinction. During that collision, matter was compressed to densities that might exceed those in atomic nuclei. Physicists running simulations estimate peak densities several times nuclear density, reaching into regimes where we don't fully understand how matter behaves. At these densities and energies, are we approaching the conditions where relativistic mass increase becomes so extreme that microsingularities form? Could these neutron star collisions be creating tiny black holes that immediately evaporate or merge with a larger system? The physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, has written extensively about extreme physics in neutron star mergers. He describes them as natural laboratories for testing general relativity in conditions we could never recreate on Earth. But there's an unsettling subtext to this research. These are conditions where the laws of physics are pushed to their absolute limits. These are the places where reality is most fragile. Think of it like stress testing a bridge. You apply more and more weight until you find the breaking point. Neutron star collisions are the universe stress testing its own laws. Most of the time, the bridge holds. Matter behaves, spacetime flexes but doesn't break, and we get neutron stars or black holes as stable end products. But what if, somewhere in the vast cosmos, the stress test fails? What if a collision happens with just the wrong configuration, just the right energy, to create a truly catastrophic runaway reaction? There's a theoretical scenario that makes physicists genuinely uncomfortable. It's called a vacuum metastability event, and it's related to the Higgs field, the field that gives particles mass. In 2012, scientists at CERN discovered the Higgs boson, confirming that the Higgs field permeates all of space. But subsequent measurements of the Higgs mass suggest our universe might be in what's called a metastable vacuum state. Here's what that means. Imagine a ball sitting in a valley on a hillside. It's stable there. It won't move unless something disturbs it. But this valley isn't the lowest point on the landscape. There's a deeper valley further down. The ball is in a local minimum, not a global minimum. If something gives it enough energy to roll over the ridge, it'll fall to the lower valley and won't come back. Our universe might be that ball. The Higgs field might be in a metastable state, and there might be a lower energy configuration it could fall into. If this happens, a bubble of true vacuum, the lower energy state, would form and expand at the speed of light, converting all matter and energy as it goes. The laws of physics inside the bubble would be different. Atoms might not be able to form. Stars would dissolve. Life would be impossible. And we'd never see it coming because the bubble wall approaches at light speed. Now here's the connection to what we've been talking about. One way to trigger this vacuum decay is through extremely high-energy particle collisions. If you create a region of spacetime with energy density high enough, you might knock the Higgs field over that ridge into the true vacuum. Physicists Sidney Coleman and Frank DeLucy worked out the mathematics of vacuum decay in the 1970s and 80s. They calculated the probability that high-energy events might trigger catastrophic vacuum collapse. The good news is the probabilities are low. The Large Hadron Collider creates millions of particle collisions, and we're still here. Cosmic ray collisions happen constantly throughout the universe, with energies far exceeding anything we create, and the universe still exists. So either vacuum decay is impossible, or the energy required is far beyond even cosmic ray energies, or we've been incredibly lucky so far. But here's the part that should make your skin crawl. Every single time a particle approaches the speed of light with significant mass, we're conducting an experiment on the stability of reality itself. Every cosmic ray collision, every neutron star merger, every high-energy event in the universe is testing whether the fabric of spacetime can handle the strain. And so far, 14 billion years into the universe's history, the fabric is held. But 14 billion years is not infinity. The universe is incomprehensibly vast, with trillions of galaxies, each containing billions of stars. Somewhere out there right now, events are happening. So here's where we are. The speed of light is a barrier that protects causality, prevents infinite energy singularities, and possibly shields us from triggering vacuum decay. But nature routinely creates conditions that push against this barrier. And the more we learn about extreme physics, the more we realize how close to the edge the universe operates. We exist in what engineers would call a narrow operating window, bounded by mathematical infinities on one side and quantum chaos on the other. The question isn't whether the speed of light could destroy the universe. The question is whether the universe is holding itself together despite constantly testing these limits, and whether one day, somewhere, somehow, the test will finally fail. But you know what's even crazier? Everything I've just told you assumes Einstein was completely right. But there are hints, subtle anomalies in our observations, that suggest there might be cracks in relativity at the most extreme scales. And if Einstein was even slightly wrong about the nature of spacetime, everything changes. What if I told you that space itself might not be continuous, that it might be made of discrete pieces, and at those scales, the speed of light might not be as absolute as we think? That's next, and I promise your concept of reality is about to get even stranger. Imagine zooming in on a photograph on your computer. As you zoom in, eventually you start to see individual pixels, the discrete dots that make up the image. Now imagine doing the same thing with reality itself. Zooming in on the fabric of space, looking closer and closer at the structure of the vacuum. What would you see? Einstein's general relativity treats space as smooth and continuous, infinitely divisible. But quantum mechanics suggests that at the smallest scales, reality might be grainy, pixelated, made of discrete chunks too tiny to see or measure with our current technology. This scale is called the Planck length, about 10 to the negative 35 meters. That's about a billionth of a billionth of a billionth of a billionth of a meter. It's so small that it makes atoms look like galaxies. At this scale, quantum fluctuations of spacetime itself become significant. The neat, smooth fabric of Einstein's spacetime breaks down into what physicist John Wheeler called quantum foam, a seething mass of microscopic wormholes, virtual particles, and space itself appearing and disappearing. Now here's why this matters for our discussion. If space is quantized, made of discrete units, then the speed of light might not be exactly constant at all energies. Photons with different energies might travel at slightly different speeds through this quantum foam. High-energy photons might interact with the structure of spacetime differently than low-energy photons. This effect is called quantum gravity dispersion, and physicists have been looking for it for decades. In 1998, a team led by physicist Giovanni Amelino Camiglia proposed that gamma-ray bursts, the most energetic explosions in the universe besides the Big Bang, might show evidence of this dispersion. If photons of different energies travel at slightly different speeds, and they travel across billions of light-years of space, by the time they reach us, the high-energy and low-energy photons should arrive at different times, separated by seconds or even minutes. So far, we haven't detected clear evidence of this effect. Gamma-ray bursts arrive with all their photons together to within milliseconds, suggesting that if quantum gravity dispersion exists, it's much smaller than early theories predicted. But the search continues. The Fermi Gamma-Ray Space Telescope and other instruments are constantly monitoring for any hints that light speed depends on energy. But here's where things get wild. If quantum gravity dispersion is real, even if it's tiny, it means the speed of light is not a fundamental constant. It's an average, a speed limit that applies at low energies, but gets fuzzy at high energies. And if the speed limit is fuzzy, maybe, just maybe, there are ways around it. Not ways to accelerate through the barrier, but ways to sidestep the barrier entirely. This brings us to one of the most mind-bending concepts in theoretical physics: warp drives and wormholes. Now, I know what you're thinking. Science fiction, right? Spaceships breaking the laws of physics, traveling faster than light through clever tricks. But here's what will blow your mind. These concepts aren't just science fiction. They're legitimate solutions to Einstein's equations of general relativity. They're mathematically possible within the framework of our best theory of gravity and spacetime. In 1994, physicist Miguel Alcubierre published a paper that changed how we think about faster-than-light travel. He found a solution to Einstein's field equations that describes a spaceship sitting inside a bubble of warped spacetime. Space contracts in front of the ship and expands behind it, carrying the ship along like a surfer on a wave. The ship itself never moves faster than light relative to the space immediately around it. But the space itself moves, carrying the ship across vast distances in arbitrarily short times. Think of it like this. Imagine you're standing on a long rubber mat. You want to get to the other end quickly. Instead of running, which has speed limits based on your leg muscles, you scrunch up the mat in front of you and stretch it out behind you. The mat carries you to your destination. You didn't move fast relative to the mat, but you crossed the distance quickly. That's essentially what the Alcubierre drive does with spacetime. Now, here's the catch. The amount of energy required to create this warp bubble is absolutely staggering. Alcubierre's original calculations suggested you'd need the mass-energy equivalent of the entire observable universe converted to exotic matter with negative mass. Negative mass is matter that has gravitational repulsion instead of attraction. It pushes things away instead of pulling them together. And as far as we know, it doesn't exist. We've never detected it. It might be fundamentally impossible. But in the decades since Alcubierre's paper, physicists have refined the concept. In 2012, Harold White and Eric Davis at NASA showed that by oscillating the warp bubble instead of keeping it static, and by optimizing its shape, you could reduce the energy requirements dramatically. Instead of the mass of the universe, maybe you'd only need the mass of Jupiter. Still absurdly impossible with our current technology, but not physically impossible. And here's where it connects back to our discussion of light speed destroying the universe. If you could create a warp drive, you'd be moving faster than light from the perspective of distant observers. But you wouldn't technically be breaking the light speed limit because you're not moving through space, you're moving space itself. The cosmic speed limit says nothing can move through spacetime faster than light. It doesn't say spacetime itself can't move. But there's a horrifying problem with warp drives that took physicists years to discover. In 2012, physicist Stefano Finazzi and others showed that warp drives accumulate high-energy particles in front of the bubble as they move. When the drive turns off and the bubble collapses, these particles are released in a burst of radiation, so intense it would sterilize everything in front of the ship. You'd arrive at your destination in a ship that's fine, but you'd be riding a beam of death that destroys your destination before you get there. Even worse, physicist William Hiscock showed in the 1990s that warp drives might be fundamentally unstable. Quantum field theory calculations suggest that vacuum fluctuations inside the warp bubble grow exponentially, creating a runaway feedback loop. The bubble might collapse catastrophically, or it might explode, releasing all its exotic energy in a blast that could rival a supernova. So warp drives, even if theoretically possible, might be exactly the kind of technology that could destroy not just the ship, not just the solar system, but potentially trigger the vacuum metastability event we talked about earlier, creating exotic matter with negative mass, warping spacetime so drastically, concentrating enormous energies into small regions. These are exactly the kinds of extreme conditions that might knock the Higgs field out of its metastable state. The universe might allow warp drives mathematically, but make them so dangerous that any civilization advanced enough to build one would destroy itself in the attempt. This is one possible solution to the Fermi paradox, the question of why we haven't detected alien civilizations despite the universe being so old and vast. Maybe every civilization that tries to break the light speed barrier discovers, too late, that it triggers their own annihilation. Wormholes have similar problems. A wormhole is a tunnel through spacetime, connecting two distant locations. Einstein and physicist Nathan Rosen described these solutions in 1935, calling them Einstein-Rosen bridges. If you could create a stable wormhole, you could step through and instantly arrive light years away. But here's the killer. To keep a wormhole open, you need exotic matter with negative energy density, the same impossible stuff you need for warp drives. And wormholes have an additional nightmare property. Physicist Kip Thorne showed in the 1980s that if you move one end of a wormhole at relativistic speeds, you create a time machine. Time dilation makes one end age slower than the other. Step through the fast-moving end, and you emerge in the past. All the causality violations we discussed earlier come rushing back. Wormholes might not just threaten space, they definitively threaten time. Stephen Hawking was so troubled by these time machine solutions that he proposed his chronology protection conjecture. He suggested that whenever you try to create a time machine, quantum effects conspire to destroy it. Virtual particles would circulate through the wormhole, building up infinite energy density and exploding the tunnel before you could use it. But Hawking admitted this was speculation. We don't have a complete theory of quantum gravity to prove it. Here's the pattern you should be noticing. Every time we find a mathematical loophole around the speed of light limit, we discover it requires exotic physics we can't access, and it potentially threatens the stability of spacetime itself. It's as if the universe has set up defenses in depth. The first defense is the light speed barrier itself, backed by infinite energy requirements. But if you try to bypass that with warp drives or wormholes, you run into exotic matter requirements. And if you somehow manage that, you face catastrophic instabilities. And if you overcome those, you risk destroying causality or triggering vacuum decay. The universe really really doesn't want anything to violate the speed of light limit. It's not just a rule. It's the fundamental organizing principle that keeps reality coherent. But there's one more possibility I need to tell you about, and it's perhaps the most unsettling. What if advanced civilizations have found a way to break the light barrier, but we can't detect them because doing so requires ascending to a higher dimension of existence? What if faster-than-light travel isn't impossible, but requires leaving our normal spacetime entirely? String theory, one of the leading candidates for a theory of quantum gravity, suggests that our universe has more than the 3 spatial dimensions we experience. There might be 6 or 7 additional dimensions, curled up so small we can't perceive them. These extra dimensions are typically described as compactified, rolled up into shapes smaller than the Planck length. But some string theorists have proposed that these extra dimensions might be accessible at high energies. If you could pump enough energy into a particle, you might knock it into a higher dimension. And in that higher dimension, the rules might be different. The speed of light limit might not apply, or might have a different value. Physicists Lisa Randall and Raman Sundram proposed in 1999 that we might live on a 4-dimensional surface, a brain floating in a higher dimensional bulk. Gravity can spread into the bulk, which might explain why gravity is so much weaker than other forces. But if gravity can access extra dimensions, maybe other things can too, at high enough energies. Now imagine an advanced civilization that learns to access these extra dimensions. They don't travel through our normal space. They step sideways into the bulk, move through those extra dimensions where different rules apply, and step back into normal space somewhere else. From our perspective, they disappear and reappear, effectively traveling faster than light. But they're not actually breaking our universe's speed limit. They're temporarily leaving our universe. This sounds fantastic, but here's the terrifying implication. If this is possible, then every high-energy particle collision, every cosmic ray impact, every neutron-star merger is potentially creating doorways into these extra dimensions. Most of them close immediately. But what if one doesn't? What if the right energy at the right configuration tears a stable hole between our spacetime and the bulk? You'd have what's called a Randall-Sundram brane collision scenario. Our entire universe, all of spacetime as we know it, could be ripped apart as it merges with or collides with another brane in the bulk. This isn't slow heat death. This is instantaneous destruction of everything, everywhere, as dimensional boundaries collapse. The probability is incredibly low, so low that physicists don't lose sleep over it, but it's not zero. And that's what makes it terrifying. We're conducting experiments with a Large Hadron Collider at energies high enough that if extra dimensions exist at certain scales, we should be able to detect them. So far, nothing. But we keep pushing to higher energies, probing deeper into the structure of reality. Every experiment that finds nothing is simultaneously a relief and a reminder that we're still testing the limits. There's a thought experiment called the quantum suicide experiment that illustrates how strange and dangerous these edge cases become. Imagine you're in a situation with a 50% chance of death every second. Quantum mechanics says the universe splits into branches, one where you live and one where you die. In the branches where you die, your consciousness ends. But in the branches where you live, you keep experiencing. From your subjective perspective, you always find yourself in the surviving branch. You might conclude you're immortal, even though in most branches you died quickly. Now apply this to the universe itself. Maybe the universe is constantly testing these limits, constantly creating situations where vacuum decay or dimensional collapse could happen. In most branches of the quantum multiverse, it does happen, and those universes end. But we find ourselves in a branch where it hasn't happened yet. We might be living in an incredibly rare, incredibly lucky branch of reality, where the universe keeps rolling the dice and keeps winning. This is called the quantum suicide approach to anthropic reasoning, and it's controversial. But it captures something important. We only observe a universe compatible with our existence. If the speed of light barrier prevents universe-destroying events, and if that barrier is occasionally violated, leading to destruction, we'd only be aware of the timeline where violations haven't occurred yet. Think of it like playing Russian roulette with a gun that has 1 trillion empty chambers and 1 bullet. You could pull the trigger 1 billion times and survive. But that doesn't mean the gun is safe. It means you've been lucky. The universe might be pulling that trigger constantly. Every time a cosmic ray hits an atmosphere, every time particles collide at extreme energies. And we're still here because the chamber has been empty every single time so far. This is perhaps the most unsettling revelation of all. We can't prove we're safe. We can only observe that we've been safe up until now. The speed of light barrier might be an absolute protection, or it might be a statistical protection. Good enough that universe-ending events are rare, but not impossible. And if it's the latter, every day we exist is another day we won the cosmic lottery. Now, I've spent the last 90 minutes walking you through the physics, the mathematics, the cosmic horror of what happens at light speed. But here's the question I want you to sit with. Why does this matter to you personally, right now, watching this video on this Thursday in October? You're never going to travel at light speed. Earth will never be hit by a catastrophic vacuum decay bubble in your lifetime. So why should you care? The answer will change how you see your place in the cosmos. Here's what most people don't realize. The fact that you exist, that you're conscious, that you're able to watch this video and understand these concepts, is itself a profound mystery intimately connected to everything we've discussed. The speed of light doesn't just prevent the universe from destroying itself. It's why you can exist at all. Let me explain. Every atom in your body, except hydrogen, was forged inside a star. Carbon, nitrogen, oxygen, the calcium in your bones, the iron in your blood, all created through nuclear fusion in stellar cores or in the explosive depths of massive stars. Those stars existed for millions or billions of years, steadily fusing lighter elements into heavier ones. That takes time. Lots of time. But here's the thing. If the speed of light were different, even by a small amount, stars wouldn't work. The balance between gravitational collapse and radiation pressure depends precisely on how fast light can carry energy away from the core. If light were slower, stars would collapse and explode before they could produce heavy elements. If light were faster, stars would burn out too quickly, again before complex chemistry could develop. Physicist Paul Davies has written extensively about the fine-tuning of physical constants. The speed of light, the strength of gravity, the mass of electrons, dozens of fundamental parameters all have values that fall within narrow ranges that allow complexity and life to exist. Change any one of them significantly, and you get a sterile universe. Maybe stars don't form. Maybe atoms don't hold together. Maybe the universe expands too fast for galaxies to coalesce. The speed of light being what it is, neither too fast nor too slow, is part of why you exist. It's why stars could form and live long enough to create the elements of your body. It's why those elements could come together in complex molecules. It's why Earth could orbit the Sun in a stable zone where liquid water exists. All of this requires a finely balanced cosmos, and the speed of light is a critical part of that balance. But there's something deeper. The speed of light creates causality, and causality allows information processing, and information processing is what consciousness is. Your brain is a physical system that processes information through causal chains. Neurons fire, signals propagate, thoughts emerge. All of this requires cause and effect. If causality broke down, if effects could precede causes, coherent information processing would be impossible. You couldn't think. You couldn't remember. You couldn't be you. The speed of light barrier protects causality, and causality enables consciousness. You are literally a product of the light speed limit. Your ability to have thoughts, to make decisions, to experience the flow of time, All of this exists because the universe has a maximum speed for information transfer. Think about that for a moment. The same law of physics that prevents the universe from destroying itself is the law that allows you to exist and think and wonder about the universe. It's not a constraint. It's not a limitation imposed on you. It's the foundation of your existence. Without it, there would be no you to be constrained. This should fundamentally change how you relate to the laws of physics. They're not arbitrary rules handed down by some cosmic authority. They're the architecture of possibility itself. They define what configurations of matter and energy can stably exist. And you are one of those configurations. You are a pattern of information processing that arose because the universe has the right structure to allow patterns like you to form and persist. Now, here's where this becomes personally meaningful. If you're a configuration of information made possible by the structure of spacetime, then understanding that structure is understanding yourself at the deepest level. When you learn about relativity, about time dilation and length contraction, you're not learning abstract mathematics. You're learning about the fabric from which you're woven. The same equations that describe light moving through space describe the causal relationships between neurons in your brain. Every decision you make, every thought you think, propagates through your neural networks at speeds far slower than light, but still governed by the same relativistic principles. Information cannot travel instantaneously in your brain. It takes time for signals to propagate. This creates the subjective experience of time passing, of thoughts flowing one after another. If information could travel backward in time in your brain, your consciousness would be incoherent, thoughts and memories jumbled into nonsense. So the speed of light doesn't just matter for cosmic scale physics. It matters for consciousness itself. It's why you experience time as flowing. It's why you remember the past, but not the future. It's why you can make decisions that affect what happens next. All of this is grounded in causality, and causality is grounded in the light speed limit. Here's an even more profound connection. Physicist John Wheeler, who we mentioned earlier, proposed an idea called the participatory anthropic principle. He suggested that conscious observers might be necessary to bring the universe into existence. In quantum mechanics, observation collapses wave functions, turning fuzzy probabilities into definite outcomes. Wheeler asked, if the universe was quantum in its early moments, who observed it and collapsed its wave function? His answer was wild. Maybe we did. Maybe conscious observers in the present are constantly collapsing the quantum wave function of the past, reaching back through time and selecting which version of history actually happened. The universe brings forth consciousness, and consciousness brings forth the universe in a self-consistent loop across time. Now, I'm not saying this is definitely true. It's speculative, controversial, and many physicists reject it. But it illustrates something important. Your existence isn't separate from the universe. You're not a detached observer looking at reality from outside. You're part of the system. You're embedded in the causal structure of spacetime. The same laws that govern galaxies govern you. And if those laws are finely tuned, if they're balanced on a knife's edge between too much and too little, between stability and chaos, then you are part of that balance. Your existence is evidence that the universe is structured in a very specific way. The fact that you're here, conscious and questioning, tells us something profound about the nature of reality. This is why studying physics isn't just about understanding external reality. It's about understanding your place in that reality. When you learn that traveling at light speed would create infinite mass, you're learning about the boundaries of possible existence. When you learn that faster than light travel would break causality, you're learning about the structure that allows you to have coherent experiences. When you learn that the universe might be metastable, you're confronting the fragility of the cosmic environment that sustains you. You're not separate from this story. You're in the story. You're made of matter that was forged in stars, governed by laws that prevent cosmic catastrophe, thinking thoughts that depend on causal relationships protected by the light speed barrier. Every atom in your body, every neuron firing in your brain, every conscious moment you experience is participating in the same physics we've been exploring. And here's what I want you to take away from this. You might feel small and insignificant when you think about the vastness of the universe, the billions of galaxies, the trillions of stars. But you're not insignificant. You're a configuration of matter and energy so complex that you can understand the very laws that govern your existence. You're the universe becoming aware of itself. Carl Sagan famously said, "We are made of star stuff." But it's more than that. We're not just made of atoms forged in stars. We're conscious patterns of information processing, made possible by the causal structure of space-time, able to contemplate the laws that created us. We're self-aware pieces of the cosmos, capable of understanding relativity, quantum mechanics, the nature of light and time. Think about how extraordinary that is. The universe is 14 billion years old. For most of that time, it was just hydrogen and helium, slowly collapsing into stars, fusing into heavier elements, exploding and seeding space with the building blocks of complexity. Then, on at least one small planet orbiting an ordinary star in an unremarkable galaxy, those elements arranged themselves into structures complex enough to think, to wonder, to ask questions about the speed of light and what would happen if we could break it. You are the product of 14 billion years of cosmic evolution, shaped by the same fundamental forces we've been discussing. The electromagnetic force that makes light possible is the same force holding the molecules in your body together. The nuclear forces that power stars are related to the particles in your atoms. Gravity, which curves space-time and creates the structure of the universe, is acting on you right now, holding you to this planet. You're not outside the system looking in. You're inside the system, made of the system, thinking thoughts that are themselves physical processes governed by the system. When you understand physics, you're understanding yourself at the most fundamental level. And here's the truly awe-inspiring part. You have the ability to change the system, not the fundamental laws. Those are what they are. But human consciousness gives us something unique in the universe as far as we know. We can make choices. We can redirect the flow of matter and energy in ways that wouldn't happen naturally. We can build civilizations, create art, explore the cosmos. We can even someday venture out beyond this planet and spread consciousness to other worlds. But to do that safely, we need to understand the rules. We need to know where the boundaries are, not to feel constrained, but to work within them intelligently. The speed of light isn't a prison bar. It's a safety rail on a cliff edge. It's protecting us from falling into mathematical infinities and causality violations that would end everything. Advanced civilizations, if they exist, must learn this same lesson. You can't brute force your way past the fundamental laws of physics. You can't ignore the boundaries without consequences. Any civilization that tries to break the light speed barrier through sheer technological force might discover too late that they've destroyed themselves. But maybe, just maybe, there are smarter ways. Maybe the universe allows loopholes we haven't discovered. Maybe extra dimensions exist. Maybe warp drives can be stabilized. Maybe we'll find exotic matter. Or maybe we'll discover that the journey, not the destination, is what matters. Maybe exploring our own solar system, understanding our own planet, taking care of our own consciousness, and the environment that supports it is the real challenge. Because here's the final truth I want to leave you with. The universe doesn't owe us faster than light travel. It doesn't owe us easy answers or convenient loopholes. The laws of physics are what they are. They've created a cosmos of staggering beauty and complexity, a universe capable of producing stars and planets, and eventually, consciousness. That's already miraculous beyond measure. The fact that the speed of light prevents certain things doesn't diminish the wonder of what it allows. It allows stable matter. It allows causality. It allows information processing and consciousness and life. It allows you to exist and think and experience beauty and love and curiosity. That's not a consolation prize. That's everything. So when you look up at the night sky and think about the vast distances between stars, don't think I can never go there because of the speed of light limit. Think I exist in a universe structured so precisely that stable consciousness is possible. I'm part of the same cosmos that contains those stars. The light from those stars has traveled across space to reach my eyes, and in that moment, I'm connected to them across the light years. You are already part of something infinite and profound. You don't need to break the light barrier to matter. You already matter. You're already participating in the grand story of the universe, understanding itself. Let me bring this all together now with a final mind-blowing connection that ties everything we've discussed into a unified whole. Stay with me, because this is where all the pieces click into place. Remember how we started? With the terrifying idea that accelerating to light speed creates infinite mass and could destroy the universe. Then we explored how light speed protects causality, prevents temporal paradoxes. We looked at cosmic rays, neutron-star collisions, vacuum metastability. We considered warp drives, wormholes, extra dimensions. And finally, we connected all of this to consciousness and your personal existence. Here's the unifying thread. The speed of light is the maximum rate at which information can propagate through the universe. Everything we've discussed, from relativity to causality to consciousness, is ultimately about information. Mass energy is information about what exists at a location. Causality is information about which events influence which other events. Consciousness is information processing. The universe itself might be, at its deepest level, made of information. This is the insight behind physicist John Wheeler's famous phrase, "it from bit." He proposed that reality, it, emerges from information, bit. Every particle, every field, every property of the universe is ultimately an answer to a yes or no question. The universe is a vast information processing system, and physical laws are the algorithms that determine how information propagates and transforms. From this perspective, the speed of light is the maximum processing speed of the universe. It's the cosmic clock rate. Reality updates at light speed. When you change something here, that change propagates outward at light speed, updating the state of the universe as it goes. If you could go faster than light, you'd be running ahead of the universe's update cycle. You'd be trying to write to memory that hasn't been allocated yet, accessing future states before they're computed. The universe would crash, blue screen of death, stack overflow, system failure. This isn't just metaphor. Physicist Seth Lloyd at MIT has shown that the universe can be understood as a quantum computer processing information according to the laws of physics. The ultimate limits on computation in any region of space are set by its energy and entropy, and those limits are intimately connected to the speed of light. You can't process information faster than light speed allows without requiring infinite energy, which brings us back to the mass energy problem we started with. So here's the revelation that should blow your mind one final time. The reason traveling at light speed would destroy the universe isn't some arbitrary cosmic rule. It's because the universe is information, and light speed is the maximum rate at which information can propagate without breaking the coherence of the entire system. Push past that limit, and you're not just breaking a speed law. You're trying to process information faster than reality can handle. You're creating contradictions, paradoxes, undefined states. The universe can't compute what you're asking it to compute, so it returns an error. Infinity, singularity, breakdown. And consciousness, your consciousness, is a localized information processing system running on the hardware of your brain, using software written by evolution, operating within the constraints of physical law. You can't think faster than causality allows, because thinking is information processing, and information processing is bound by light speed. When you understand this, you realize that the laws of physics aren't limitations on what you can do. They're the preconditions for your existence. They're not walls around a prison. They're the foundation of a cathedral, and you're part of the architecture. Everything in the universe, from the smallest quantum fluctuation to the largest galaxy cluster, from a single thought in your mind to the collective knowledge of civilization, is part of one unified information processing system we call reality. And that system has a maximum operating speed, the speed of light. Violate that speed, and you don't just move fast. You violate the fundamental architecture of existence. You create undefined behavior in the cosmic computer. And when computers encounter undefined behavior, they crash. The universe has been running for 14 billion years without crashing. Stars form and die. Galaxies collide. Black holes merge. Life emerges and evolves. Consciousness appears and wonders about it all. None of these processes have crashed the system because none of them violate the fundamental constraints. They all respect the speed limit. And as long as we respect it too, as long as we work within the boundaries of what the universe allows, we can continue to grow, explore, create, and understand. We can build civilizations that span solar systems. We can unravel the deepest mysteries of quantum mechanics and cosmology. We can even, perhaps, find clever ways to work with the structure of spacetime rather than against it. But we'll never break the light barrier through brute force. And maybe that's okay. Maybe that's more than okay. Maybe that's perfect. Because the light barrier isn't keeping us from anything we need. It's protecting everything we are. So here's my challenge to you. The next time you see light, whether it's sunlight streaming through a window, or the glow of a screen, or the twinkle of stars at night, remember what you've learned. That light is traveling at the cosmic speed limit, the maximum rate at which information propagates, the boundary between possible and impossible. And remember that you exist because that boundary exists. You think because causality exists. You experience time because light speed is finite. You're not separate from the physics. You are the physics. You're a self-aware pattern in the cosmic information field, asking questions about the very structure that makes questions possible. And that, more than anything else, is why the speed of light matters. It's not about rockets or travel or conquering the stars. It's about understanding the nature of existence itself and recognizing that you, right now, are part of the most extraordinary phenomenon in the universe. Consciousness arising from matter, life emerging from chemistry, understanding growing from experience. The speed of light could destroy the universe if violated. But more importantly, the speed of light creates the universe, sustains it, structures it, and makes everything we know and love possible, including you. That's not a limitation. That's a gift beyond measure. If this video changed how you see reality, hit that like button and subscribe because we're just getting started. Drop a comment telling me which part blew your mind the most and what you want to explore next. And remember, you're not just watching videos about the universe. You're the universe watching itself, learning about itself, one mind-blowing revelation at a time. Thank you for joining me on this journey to the edge of possible and back. Stay curious, stay amazed, and I'll see you in the next video, where we'll dive even deeper into the mysteries of existence.